Hey class, today we're going to go over acid-base reactions. This is lecture 34, and just kind of by way of announcement, there's like 2 more lectures after this before I do the final exam review lecture. So we're getting close to the end here. All right, let's get started on this one. All right, we're going to learn about TUMs a little bit today, and I mean there's a lot of different kind of like antacid type stuff and how those work, and talk a little bit about different acid-base reactions that you might be familiar with. To start out, we'll go ahead and try this quiz, so pause the video and try it out. All right, this should be a review from the last lecture. So let's see, we got the hydroxide concentration of a solution is 5.3 times 10 to the negative 3 molar. What is the pH? So in the last lecture, we learned pH equals the negative log of the hydronium concentration, right? And we're given the OH concentration, but we can use this relationship to find the, sorry, that should be hydronium concentration. So we can use the OH minus concentration to find the hydronium concentration, which we can then plug in to this equation to get the pH, okay? Perfect. There you go, those are all the steps laid out. Okay, so we find the hydronium concentration, plug it into this equation, and get 11.72. Okay, and the other option is to use POH. So that's just going to be the negative log of the OH concentration. And then you do 14 minus that, and you get the same answer. So whatever way you're most comfortable with at this point. Okay. So the goal of today is to understand patterns and predict products for certain acid-base reactions. Okay, so what happens when we mix an acid and a metal, or an acid and a carbonate, or an acid and a base, okay? Okay, so the first one is mixing acids with metals. Okay, so when an acid reacts with a metal, it produces hydrogen gas and a salt. So our metal here is potassium. Our acid is hydrochloric acid. We're going to produce a salt, right? And then we're going to produce hydrogen gas. So the salt consists of the metal, which was potassium. All right, so maybe I'll just write these out. So we have our metal, we have our acid, we have a salt, and we have hydrogen gas. Okay, cool. The salt consists of the metal, which is potassium, and the conjugate base of the acid, which is chloride. Okay. Back up a little. Okay. All right, so here's just another example. Zinc is our metal, hydrobromic acid is our acid. We're going to have our metal with our conjugate base, and then hydrogen gas. And of course, when you make these, it's not necessarily a 1-to-1 ratio. Zinc forms a 2+ ion, and bromine forms a 1- ion. So you're going to need 2 bromines with the zinc. We've seen that before with ionic compounds. Okay, I think that's it for that. All right, so I'll go ahead and try this quiz out real quick. Okay, so this is which compound was reduced in this reaction. So we're doing a little bit of review from our oxidation reduction. All right, we want to review this stuff as we move towards the final. But zinc starts, it's by itself, so it would have a ground state or 0, and then it moves to the +1, or sorry, moves to a +2 charge. Okay, so if you remember oil rig, right, reduction is gaining electrons. Zinc is actually losing electrons to come to the +2. So zinc is oxidized, which means this would be the reduced compound. Okay, cool. All right, we're gonna predict the products here of the reaction. Go ahead and try this one out. Okay, so we talked about how metals plus acids give you salts and hydrogen. Water, we talked about how it's amphiprotic, right? It can work as an acid or a base. So in this situation, we're going to say it's an acid. I think the easiest way to look at it is to draw it like HOH, okay? So you can see that if it loses a proton, it becomes hydroxide. Okay, so again, we have our metal mixed with the conjugate base. The conjugate base of water is going to be hydroxide. Okay, and then we should have hydrogen gas. Okay. Awesome. So E would be our answer. Perfect. Okay. All right, another quiz. And keep got quite a few quizzes in this lecture. Keep you guys on your toes. All right. So this says, what reaction do we expect if we add HCl to sodium carbonate? Okay. So this is kind of, I guess, foreshadow of what we're going to learn in the next slide. So we'll talk about this. But carbonates with acids are going to produce salts, water, and carbon dioxide. Okay. So when we have acids reacting with carbonates or bicarbonates, we're going to produce CO2, salts, and water. Okay. So for example, here we have our acid. Here we have a carbonate. Okay, right, and the reason I say carbonates because this could be sodium carbonate or calcium carbonate or any number of different carbonates, right? But CO3 is common. CO2 is going to be our carbon dioxide gas, and then we have the salt, which consists of our metal, right? So the metal that we have in this reaction is calcium, and the conjugate base of the acid, conjugate base of HCl is just Cl minus, right? So that's the conjugate base. And then we have water as well as a product. Okay, so this is true for a lot of these. So this carbonate is going to be a lot of acid-base reactions that you're familiar with. Follow the acid and carbonate reaction. For example, calcium carbonate with HCl. So carbonates are what you see in like Tums and Rolaids and stuff like that. And HCl is your stomach acid. And so when you have heartburn, right, some of your stomach acid is coming up your throat and it gives you like that burning sensation. Don't know. Some of you may have had it. Some of you may have not had it at this point. But when you take the Tum, okay, so you take your Tum, it's going to go into your throat. It's going to mix with the HCl. It's going to produce carbon dioxide, a salt, and water. So you can see how acid, which is going to have a low pH, gets neutralized to water, which has a neutral pH. By doing that, you have less acid in your throat, and you can reduce the effects of heartburn. Okay. Carbon dioxide just turn to a gas and probably come out when you breathe, right? Because you breathe out carbon dioxide anyway. And then you just have this salt that just go down to your stomach, just like table salt water or whatever. Okay. Let me back up. Okay, so here's another example where you have hydrochloric acid with sodium bicarbonate. Again, bicarbonates do the same thing. Form carbon dioxide, salt, and water. All right. Go ahead and try this quiz question out. Okay, so this says, what volume of carbon dioxide gas is produced at STP when 125 milliliters of 0.1 molar nitric acid reacts with calcium carbonate? All right, so now we're going back into stoichiometry. Okay, so if you look at your stoichiometry map, if you guys have those handy, we're going from nitric acid here, and we're going to go to, let's see, carbon dioxide. Okay, so this would be our A and our B. Okay, so we're starting with a volume of A as a solution. So 125 mils, I'm going to turn that into liters. So it's 0.125 liters of nitric acid, Na. Okay, so for every 1 mole of nitric acid, we have 0.10, oh sorry, for every liter, we have 0.10 moles of nitric acid. So this is just using the molarity here. So 0.1 moles per liter. Okay, and then we could convert from moles of nitric acid to moles of carbon dioxide using the molar ratios. And we need milliliters. Oh, and it's at STP. So at STP, we can use 22.4, sorry, 22.4 liters per mole, right, of CO2 gas. Okay. Sorry, I don't know why I'm running moles here. 22.4 liters of CO2 for every 1 mole of CO2. Answer that and you get your liters out. Okay. So this is going to walk through it here. So we got our volume times molarity gives us moles of nitric acid, convert to moles of CO2. And we can use 22.4 liters per mole to get us to the liters of carbon dioxide. Convert that to milliliters and you got answer B. Okay. Okay, so the last reaction we're going to talk about is neutralization reaction. So that's going to be where an acid reacts with a base and it forms a salt and water. It forms salt water. Okay, so here's your acid, your base. Your salt is just going to be the conjugate base and the metal from the conjugate base of the acid, which is chloride, and then the metal from the base are going to combine to form your salt, and then you got water. Okay. So the reason these are called neutralization reactions, right, is because water we talked about has a pH of 7, and that's called a neutral compound, right? Okay. Okay, so balancing these reactions, I'm going to kind of show you the easiest way to do it. In the end, just like any other equation, you need to have all the elements balanced on the left and the right hand side. Okay, but let's say you're given this neutralization reaction, right? Magnesium hydroxide is a base, nitric acid is an acid, and you're going to form the salt and water. Well, the easiest way to do this is to notice that your acid is going to give off 1 proton. And when magnesium hydroxide goes into solution, it's going to give off 2 OH minuses. So that tells me for every one of these, I need to give 2 protons, right? Because I need one proton will neutralize one of these OHs, and then we need another molecule of nitric acid to give off another proton to neutralize the other OH, okay? So you want to make sure the moles of OH minus match the moles of H plus that's given off. So you put a 2 in front of the nitric acid in order to balance that out. And then if you just look, and so then you know that this part on the left side is balanced, right? 1 magnesium, and then you can count all these up, right? We have 2 oxygens here and 6 oxygens here, right? So that tells us that there's a total of 8 oxygens, okay? And then there's 2 hydrogens here and 2 hydrogens here, so there's 4 hydrogens, okay? 1 magnesium on the left side and 2 nitrogens. Okay, so then, all right, so we want to make sure that's balanced on the right side. So we have 1 magnesium here, so we're good. We got that. We have 2 nitrogens and 6 oxygens. So we have the 2 nitrogens, so we don't want to mess with this one here. Here we have 4 hydrogens, right? Oh, sorry. If we didn't have the 2, we would have 2 hydrogens, right? And we need 4, so we put the 2 in front of it. That gives us 4 hydrogens. 2 oxygens plus the 6 gives us 8 oxygens, so now we're balanced. But these are pretty easy to balance compared to what we've done before, because you really just make sure the OH minus and the moles of H plus are balanced. And then you just kind of adjust the right side to make it match. Okay. All right, go ahead and try balancing this equation here. Okay, so select the correct group of coefficients needed to balance the following neutralization reaction. Okay, so you can see that H3PO4, so phosphoric acid, actually loses all 3 hydrogens that it has, right? So this gives off 3 hydrogens. The barium hydroxide has 2 hydroxides to give off. So there's the 2 and there's the 3. So in order to balance these, we would need 3 barium hydroxides and 2 phosphoric acids, right? That gives us a total of 6 hydrogens, or H pluses, I mean, and 6 OH minuses coming off. So that's balanced. Then we can just look at these ones and make sure we balance them correctly to match the number of elements on the left side. Okay, so really just need to adjust the water molecules in this example. So 3, 2, 1, 6, okay, should be B. All right, so again, we talked about this, but antacids are bases that neutralize stomach acid. So here's just a few of the different antacids that you could buy, like medicines that work to do this. The most common is Tums or Rolaids, and they all use calcium carbonate. Sodium bicarbonate, right? This is baking soda. Okay, so in a pinch, if you have heartburn and don't have Tums, but you have baking soda, you can make up a little, mix some of that in some water and drink it. Probably tastes terrible, but it would work. And this reaction is really common in cooking, right? So, oops, sorry. So when you make like really anything that has baking soda in it, right? Like cookies, or what else is baking soda? I don't know, because I don't cook enough. Cookies has baking soda in it. So the cookies are for the baking soda in the cookies, or it might have baking powder, right? Which I believe baking powder is mixed with an acid as well. So baking powder, I believe, consists of baking soda and acid. Let me just double check real quick. Okay, yeah. So baking soda is, sorry, I paused the recording. So anyway, baking soda or baking powder has some baking soda in it and a weak acid, and another, I think, cornstarch that's mixed in a little bit to keep the base and the acid from reacting too much when they're sitting there. But once you put them in a solution or like cookie dough or something, that base and that acid are going to mix together, and they're going to start forming, it's a carbonate and an acid, so it starts to form carbon dioxide, and that causes the rise in cookies and stuff like that. So anyway, it's something to think about when you're making cookies this weekend or whatever. Okay. Okay, yeah. So our goal, again, at the beginning of the lecture was to predict products of common acid reactions. So acid plus metal equals salt and hydrogen gas, acid and carbonate, salt, CO2, and water, and acid base is the salt and water, right? This is the neutralization reaction. And then be able to balance these reactions. These ones are almost always just like, not always, but commonly they're kind of balanced as you write them, but you can go back and balance them if you need to. But anyway, things to pull from this lecture: know these 3 types of reactions. So given an acid and carbonate, be able to predict the products, or for any of these, right? Given the reactants, be able to predict the products and then balance the equations. And that's kind of the main idea to pull from this lecture. We're going to do a couple practice problems here to help with the homework. You can kind of see like the lectures at this point in the class are like fairly simple. I feel like there's like a small amount of ideas that are presented, but then we go back and we apply them to everything we've learned before, and that's where it gets complicated, is applying it in new ways. So let's go ahead and practice some of that. It's at the end of this lecture. So this question is a stoichiometry question, obviously. It says how much 0.225 molar sodium hydroxide is required to neutralize 18.5 mils of 0.425 molar hydrochloric acid. Okay, so we need to know basically how many moles of hydrochloric acid are going on here. So let's say we have 18.5 milliliters, and then, well, let's convert that to, let's use liters, 0.0185 liters times the molarity of HCl. So 1 liter HCl to 0.425 moles of HCl. When we do that calculation, we're going to get moles of HCl, right? Okay. So now we know how many moles of HCl that we have, and because there is a 1-to-1 ratio here between the acid and the base, the moles of sodium hydroxide needs to match the moles of HCl. So let me just do this calculation real quick. Okay, so 0.0185 times 0.425. Okay, so we get about 0.008 moles of HCl. Okay, and then we can say that we have, actually I should probably use more sig figs, so 0.00786 moles of HCl. Now the moles of HCl and the moles of sodium hydroxide, again, to neutralize them completely is a 1-to-1 ratio. So those moles are going to be equal. So I can use the fact that basically for every 1 mole of HCl, we're going to have 1 mole of sodium hydroxide. So I'm going to say 0.00786 moles of sodium hydroxide. Okay, and then I'm going to flip around this molarity. We don't do this too often, but you can because it's just a conversion factor, right? 0.025 moles of sodium hydroxide for every 1 liter of solution of sodium hydroxide. Okay, right now those moles are going to cancel out. We're going to be left with liters of sodium hydroxide solution, which is what it asks. How much sodium hydroxide solution, right? It's implied it's a solution because there's molarity. All right, let's see back it out and see what the slide does here. Okay, so again, we're going to figure out, go from liters of HCl solution to moles of HCl, and then use that conversion, that moles of HCl and moles of sodium hydroxide are going to be equal because there's a 1-to-1 ratio. And then use the molarity for the sodium hydroxide. See that for 0.225 moles of sodium hydroxide, we have 1 liter solution, and then we can get the answer out. Okay. All right, go ahead and try this one on your own, this quiz question. Okay, so it says how much 0.1 molar calcium hydroxide is required to neutralize 25 mils of a 0.3 molar nitric acid. Okay, so on this one, it's going to require us to kind of write a few things out. So calcium hydroxide is required to neutralize nitric acid. Okay, so NHO3. Okay, and then balancing this, we know we need, this only gives 1 proton and this gives 2 hydroxides. So we need 2 of these. We're going to form calcium nitrate and water. And we probably need 2 waters to make that work, right? So we have 4, say 2 hydrogens, that's 4 hydrogens. Okay, so we need 4 hydrogens, okay? So that's our balanced equation right there. All right, so now we can kind of just walk through the same steps as we did last time. So we have 25 mils of 0.3 molar nitric acid. So I'm going to say 0.025 liters nitric acid. and then use the molarity, 0.30 moles of nitric acid. And then for every 2 moles of nitric acid, we have 1 mole of calcium hydroxide. Okay. And then let's see. Oh yeah, we have this molar solution. So 0.10 moles of calcium hydroxide for every 1 liter of solution. Okay, and then we should be able to get our answer there. So here's the PowerPoint doing it basically. Let's see. Oh, I think the PowerPoint's off a little bit. It says 0.3 moles of calcium hydroxide. I think this should be nitric acid. Okay, yeah, don't pay attention to this. I kind of messed this up. What I wrote before was better. Okay. Oops, so the answers might be off, but we got through the process, and that was the important part. Okay. Go ahead and pause the slide and try this one out as well. All right, so it says we have 10 mils of HCl at an unknown concentration. Okay, that's not too helpful, but we'll keep going. We find that it takes 16.5 mils of 0.225 molar sodium hydroxide to neutralize the HCl. What was the HCl concentration? Okay, so write out the chemical formula, or sorry, the balanced chemical equation first. So we're doing a neutralization reaction. So hydrochloric acid is going to combine with sodium hydroxide. It's a base and an acid, so that's a neutralization reaction, and you form a salt. So we don't know much about HCl. It's probably where we're going to be moving towards, but we do know, let's see, that it takes 16.5 mils of 0.225 molar sodium hydroxide to neutralize. So sodium hydroxide would be our A, HCl would be our B. So we're moving from volume of A, right, down to moles of A. This is if you're following on the stoichiometry map for these problems. I just want to show you to volume of B, right? And then this transition uses the molarity, and this is the molar ratio. This is what we've done in the last couple problems. The only problem here is we can go from volume of A to moles of A, and moles of A to moles of B really easily. We don't have the molarity to go from moles of B to volume of B, right? But if we know the volume of B, sorry, we know the moles of B and the volume of B, we can actually just divide those two to get to the molarity. So let's follow this through. So we're starting with our sodium hydroxide solution, right? The volume and the molarity, and that gives us to moles of sodium hydroxide. Use the ratio to go to moles of HCl. And then you could stop there and solve for moles of HCl and then just divide by the volume, or you could do it all in one line. Here where we're saying we have 0.1 liters, right? That's 10 milliliters of HCl. So our liters cancel, moles cancel, and we're left with moles of HCl over liters of solution, right? And then that's the definition of molarity, basically. So you can see kind of like using your units, it helps you work through these problems if it doesn't fit perfectly on the math that we use. Okay. All right, hopefully that was helpful, and we're getting some of this acid-based stuff. Again, I don't think the ideas are terribly in depth in the lectures, but we kind of wrap it back and apply it to what we've been doing so far. And so it's good in that way we get some review, but also sometimes a little tricky when you tie it into other topics. So keep practicing that as you're moving along, and I'll see you next time.